So this is going to be a lot of fun. I say that with most of my live streams. I'm going to attempt to convert our unbalanced binary tree, the one that I wrote, that ChatGPT wrote for us in last week or the week before. Last week. We're going to try to convert that to an AVL tree and then to red-black tree. Last time I wrote an AVL tree was, I think, 1990 or 1991. I can't remember if it was first or second year university, one of the two. I think it might have been both, actually. I'm quite sure I did a data structures course in first year. But it was a long time ago, and what's it, 30... How long is that? That's a long time ago, 34 years ago. So I understand sort of the principles and where we want to go, but I wouldn't be able to do it. Like if I went for a job interview and they said, write an AVL tree, I would say, sorry, mate, I can't help you on that one. You'll have to find someone who's more recently finished their computer science degree to be able to do that. But let's see how well we can do this with ChatGPT. Right, so we've got our simple unbalanced binary tree, and if you want to have a look at my at all the previous codes, look at my GitHub repository, GitHub/Karbut, and you'll see there's a Java specialist on Twitch. I'm streaming to Twitch and LinkedIn and Twitter and a private Facebook group for my Teachable students. So yeah, there are quite a few different places, and LinkedIn as well. So there are quite a few different places it goes, and you can gladly grab the code and look at it, or you can just ask ChatGPT to generate that for you, and it'll be just the same, pretty much the same. So here's our code, and what I want to do before I start, I actually want to extract an interface. This is not really AI. This is what we've been doing all along. So if we go to refactor, I think is the right thing. I need to get to the menu. This is on another screen, so one moment, bear with me once I find the refactor. Refactor, and then it's extract interface. Extract interfaces. There's probably a shortcut for that to do that. But alright, so the interface name, we're going to say we're going to rename the original class. So the interface name is going to be called just binary tree, like that. And we're going to have add in there, implements iterable, we'll do that as well. I don't know about node and pair if we need those. I'll leave those out for now because they might be different for each of the different implementations. Contains, remove, iterator. Actually, iterator we can leave out because that'll be implemented by each of the subclasses, and then size and max depth. Remember in the previous stream we did the max depth so we could confirm that our tree, which we thought was actually unbalanced, was actually quite well balanced because of randomness. But that's what we're going to use. And then I'm still using the same package, EU Java Specialist Twitch Broadcast 1. So of course we've done quite a few broadcasts by now, but so let's try that. And okay, and then what I also want to do is I want to change my test, the simple tree test, and this will be very similar to the way we did our simple list test. The simple tree test will have a method create which is going to return a binary tree. So that's what we're going to return, the binary tree. And we'll have a simple unbalanced binary tree test. Simple, let's copy this to simple unbalanced binary tree test, which extends the simple tree test. Extends simple tree test. And it's going to only override the abstract method, which is not abstract yet, but we'll make it abstract, which is this one over here. It's going to be protected, abstract, binary tree, create. So let's make the class abstract and delete the method body. All right. So this is the abstract class simple tree test. We've got the simple unbalanced binary tree test, which extends simple tree test. And what else do we have here? We've got our all we need to do is to have the create method, and everything else will be just simply inherited. Now we might have to override some of the methods to not do anything because, well, let's just see. Let's just run it and see what happens. For now, this test should run, I think, because all we're doing is we've just moved the interface up. So the test runs. The unbalanced contains some max depth over here. Actually, this is not really unbalanced. This is randomized. So I've shuffled the list so that the name is not quite accurate. If I take out the shuffle, then what we'll see is that it's going to be fairly slow. The unbalanced contains a max depth of 10,000, and so we'll leave it that way without the shuffling. Because we want to demonstrate what happens when we've got an AVL tree. And AVL stands for some people's names. I actually had a look in ChatGPT early on what it means, and some people's names. Of course, I've immediately forgotten them again. So we'll take this out of here, and that's our very similar. It prints out the depth, which is 10,000 if it's unbalanced, and it's quite slow. All right, good. So that we'll start here. We'll say just extracted. Binary tree interface, and we've also got this separate test now. So now that we've done that, we're going to try and convert this to an AVL tree. So it's going to be AVL, and AVL is a fairly costly tree to maintain because each time you add a new item, you need to then rebalance the tree. So it means you need to rotate rotate nodes and so on, and sometimes recursively go all the way back to the root and rotate that as well. So there's a fair amount of rotation going on, but with the AVL tree, you should be pretty close to the optimum in terms of depth, which means if we have 1 million entries, it shouldn't be more than 20 levels. Might be a few more than 20, I think, but it'll be pretty close to 20. Whereas with the red-black tree, which we'll do after that, with the red-black tree, we're going to instead use that. The red-black tree has a maximum of 2 times the optimum depth that we could have for a binary tree. So it's a bit less efficient, but it's a lot easier to do. All right, but we'll do this very easily. We'll simply select this, and we're going to use our trusty ChatGPT again. So Alt-Enter, AI Actions. No, I'm still can't figure this out, how and when this is supposed to work. Generate code. I'm going to say convert to an AVL tree. Let's do this. Let's say adding javadoc comment explaining how the AVL tree works and why it is called an AVL tree. So I'm being very specific what I want, and we'll see what it what it generates. Oh, there you go. It's got the names: Adelson, Velsky, and Landis. Sorry, Adelson, Velsky, and Landis. Of course I forgot what it, but at least I remembered the name, AVL tree. So this goes and now goes and writes this for me. And as I said, I've done this. I mean, I've done this a long time ago. I don't want to do this again, write code like this again. But I did it, as I said, 1990 or 91 or both, probably both. Back in the day, you couldn't just do this with AI. You had to actually write the code by hand in C or Pascal. I can't remember which one it was. I think it was C. But there we go. It's generating all of it. And then once we're done, it's still busy. Then we'll try it out. We'll do a test as well and make sure that the test works. If it works, I've got no idea. But let's see how it goes. So we're done. Okay, so let's say accept all, and it's not very happy with anything. Okay, so what's not happy with? It's not happy with implement contains. Well, actually, the contains should be a fairly easy method to write. The part which is difficult is the right, rest of the code, ... Well, yeah. Why didn't you just do it? I mean, contains is really easy. The hard part is the remove and the add. So add is tricky. Oh, come on, seriously, why didn't you do all of the methods? I tried it out early on, and I think it actually created all of the methods. Let's do generate code and say, this just doesn't, as I said, for some reason I can't get these shortcuts to. Okay, add missing methods to complete the binary tree interface in our AVL tree. Let's see if it generates the rest of the code. So we'll see how well it works. Oh, so for contains, it's done. Now, contains should be very easy. The contains should actually be pretty much the same as before. The problem I've got is with remove, because remove needs to rebalance as well. So okay, so we don't want to delete the comment. The comment actually I want to keep. So the comment we want to have. So, but I do want to have the contains. So let's copy that over, the contains, and the remove. Oh, maybe I should be a bit patient there. Okay, let me just say accept all and see what it does. Okay, now it's destroyed it again. Okay, that didn't work. That didn't work too well. Let me undo this all and go back to what we had, and be a bit more simple in my request of what I want. Because the thing is, what I might want to do is to go, okay, I actually want to do back to this one here to, let's just go back to this code. In fact, let me delete and start again. So, let's try this. We'll do, you know what I could try? Actually, I could try and simply start from scratch. Instead of converting my existing binary tree to my unbalanced binary tree to AVL tree, I could try to do it this way. So let's do over here, let's do AI actions, and we're going to go generate code, implement an AVL binary tree, and see what it does. And see if it actually adds all the methods, the remove and the iteration and all of that stuff. So that didn't really do what I wanted. It's trying to change my interface, whereas I want to implement the class to do it. So create a subclass that implements an AVL binary tree. Let's see if that works. Okay. Implementation of AVL tree goes here. Thank you very much. Yeah, that's exactly what I want. Right, but I actually want you to write it. Okay, so let's try this again. We'll do implement interface, AVL binary tree, and now we're going to try to do it with AI. Actions, generate code, implement an AVL tree. Let's see if it does it. It's of course all about prompts. You know, if you get the prompts right, you get the job done. So this is now completely from the beginning, without taking the existing binary tree and rewriting it. And we'll see whether it actually does it implements all the methods, not just some of them. So there's right rotation, left rotation. As I said, I don't remember the stuff. I vaguely remember it. It's like, and I had to look at my bookshelf. I've got the book somewhere that we used back in 90 or 91, but I think it's downstairs in my son's room. He was doing a C course, and seeing it's, C hasn't really changed that much since I studied it. So I've got insertions here, rebalancing. We'll see what comes up. What's it comes up with? I'm probably okay. So it hasn't implemented all the methods. I need to implement all the methods as well. So this now accept all. Alright, so it's got insert. I want to call it add rather. And it's weird because it's like add. Rename it rather. Add. Okay. So we're still missing a bunch of methods here. We're missing the methods contains, remove, size, max, depth, and iterator. All right, let's see if it's smart enough to add those. Let's just type add a remove method. Okay. Add a remove method. The remove is a hard one because that changes it, and it would need to be rebalanced if it changes it. The contain should be trivial. The max step should be trivial. Max step should be basically the same as before. So an even iterate, I think, should be the same as before. So I might copy those over from the previous code, or maybe even one could even put them into the super interface. Although that would be a problem because then I need to have node as a common class, which is not going to work because it would have to be then publicly accessible, which I don't want to do. Okay, so you can't use protected inside an interface. So let's see, remove key, remove root key, removes a key, and it does the comparison. I want to see if it does a rebalancing because it needs to rebalance it. To simply remove it is not going to be enough. It needs to also rebalance it. So it looks like it's doing some height over here, and it does some rebalancing. So it looks like it's doing it the way that I want it to work, which is good. So it's rotating and so on and so forth. Good. So it's doing the hard work, which I don't want to write because I escaped from university. I want to go back there. What's the point of that? Let's accept that. I'm going to copy the other code over. So the contains, I think, will work as is. Let's try that. So let's copy this over. Copy and paste. Very, very fast way of writing code. So this node isn't... Okay, I'm going to make this a static class over here with its own t. And I think that's okay. I don't think I need compare to node.key. Yeah, that's a different key, different t now. So it's a bit different the way that the node works. So let me undo that again and try to see if I can fix this contains code. So contains would just be node, not node t current, and it'd be current dot key, I think, and dot key. So let's rename that to value because I think it's a better name. Okay. So we've got a node. Now is more similar to before. It's got a value, got a height. The value we can probably make final. Is that possible? No, we can't. Okay, so we've got to keep it as non-final. So we'll leave that as it is. The other part, which should be fairly simple, should be the iteration, because it's just going to do, and the depth calculation as well. So let's go and just copy the iterator method over. We're not removing, and the size and the max steps we'll copy over as well. And remember, last time we actually made the max steps to be iterative rather than recursive, which we shouldn't need with this tree, because we can never become that deep. Right? Oh, and I've done something else here. No.value. Oh, I thought I made it non-final. Oh, we take that out again. I changed the final, but that didn't work, so we got rid of that. So let's put in the contains and try and fix it to work. The contains, the iteration first of all, is my iterator over here. And we need we don't have a mod count at the moment. We need to add a mod count. Oh my goodness. Yeah, that's tricky. So generate code, make AVL binary tree fast fail on iteration. See if we can figure that one out. Might be easier to just add iterator to it. So we add the mod count, which will then hopefully get changed whenever you add or remove something. So in the add, we have the mod count. Let's pop that in there. I just want to actually copy the one thing over. I don't know if that was correct or not. Let me just cancel that. And I've destroyed everything. It's deleted one line which I shouldn't have deleted. Well, one of the fun things here is that you actually can't really practice for these in live streams, because it actually worked quite well before when I was doing the practice. And then what's also weird is when I do the AI, then it doesn't seem to like undoing anymore. So the undo doesn't work as well as it did before. So this, we need to put this back, and then we're going to add a mod count, and I'll just have to put it in manually. So put in here private int mod count equals 0. Start at 0, and in the add we're going to say mod count plus plus after we've added it. So mod count plus plus. Similarly in the remove, once we've removed it, we're going to say mod count plus plus. And then we should be able to use a mod count in the iteration to check whether it's been modified. I want to rename it to, okay, I wasn't sure whether it was mod count with a big C or a small c, but it's supposed to be big C, so let's change that to be a big C. Alright, mod count. Alright, let's see what else it doesn't like. It doesn't like the T, let's get rid of that. The Q must be imported. More generics it doesn't like. More generics it doesn't like. It must import the array deck. And you can say array deq or array deck. I believe the correct one is array deck. Alright, we've passed all the errors. Now let's see if it actually works. Oh my goodness, this is tough. Now let's go to the test, and we've got a simple unbalanced binary test. We're going to copy that to the simple AVL binary tree. Actually just AVL, not simple. There's nothing simple about it. And I haven't actually looked at the code yet. I'm just hoping it works. AVL binary tree. And let's run that and see what comes out. Whoa. Okay. Well, that's interesting. Huh. So the first part is the depth. Now the depth is, we've got 10,000 elements, we've put them in, and of course the max depth is not going to be 10,000 in this case. It's going to be log n of that. Now log n of 10,000 divided by 2, let's say jshell math.log there was another one. There was log 10,000 divided by math.log 2. It's 13.28. So it has to be 14. 14 is the, it's got to be rounded up. So 14 is the best we can do on that. So 10,000. Actually, that's correct. So the assert equal size is this is not a correct test. We can't do it this way. We could have a method called protected int expected max depth int elements, and this would be an abstract method. All right, and then what we can do in here inside assert equals, we can say expected max depth of size. Right? No, that's wrong. Yes, that's right. That's right. That's what we're expecting, and then we pass in the max depth. So now what we can do is we can go to our unbalanced binary tree. We can override that method, and we can say we can actually expect this to be return elements, right? And the AVL tree, binary tree test, will override that, and we'll say expected max will be return math dot log. It's only got log. I'm thinking of Excel or who have other log functions, but we'll just do log elements divided by math.log 2, and then we need to get a ceiling on that, so it's going to be math.ceil on that, so it's going to be rounded up to the nearest closest one. So now it should work. Now it should be 14. Okay, so that passes. And the other thing which fails is the iterator. The iterator, I'm not sure about that now. I'm not sure about that. Expected is, yeah, that's interesting. The iterator, I think, is simply, what is it going to do? What does a default iterator do? I'm not sure, actually, to be honest. And I'm not sure. It should be sorted. I think iterator should be sorted. The AVL binary tree should be sorted. So I'm not sure about this one. I'm going to comment this out for now and just look at the other tests. Right, so the AVL binary tree test, if we run that, everything else I think should pass. Everything else passes. That's good. And the simple tree max depth is 14 now, and the time is 21 milliseconds, versus if you take the unbalanced binary tree test and you run that, then the max depth is 10,000 and it's like 9 seconds, so it's much, much slower. And that's what we tried to show in the previous live stream. We're looking at that in great detail, so have a look at those if you're interested. All right, so where are we now? The iterator, I want to quickly look at that because if you look at the simple unbalanced binary tree, the way the iterator works, it goes and what does it do? It basically creates, oh, this is interesting. They're using a trick which I wrote about a very long time ago with this linked list. I didn't actually look at the code, but this over here is a trick which I wrote about in 2000. I think it was 2000. And I think I'm quite sure that was the first time that it was written about. Let's go right to the bottom. it was 2000 or 2001. It was it this one? No, it wasn't this one. It was right at the beginning. I think it was this one, 2000. So this one here, anonymous inner classes. So it basically showed how you could initialize, for example, a vector. Because at the time we had vector, we were using vectors a lot. Here we made new vector and then have two curly braces, and then add them in there. I wouldn't do that nowadays. I've repented of that. I know that Morris Naftalin and Phil Wardler wrote about this in their book. They copied some of my ideas into their book, Data Structures and Generics. They gave credit, of course, but I certainly wouldn't do that nowadays. I would write it quite differently. I would do it differently. I'd just say something like this. I'd say, because what we want to do is we basically want to initialize the whatever this is. Now I'm going to use not a linked list but an array deck rather. And rather than doing it this way, I'm rather going to have a separate initializer block like this afterwards. Because otherwise what I'm doing is I'm making a subclass of array deck, which is unnecessary. I don't really need to do that. And I can just say here nodes.add root. So I think this code is a bit better. And I'm going to do the same in the unbalanced binary tree. Because I just copied it over, so it should be, oh, that was the unbalanced binary tree. I mean, do the same thing here. So I don't like this anonymous inner class, subclass of linked list. Where's the iteration now? Here it is. So I'd rather do something along these lines. So the funny thing is, like, it's actually taking some bad ideas of mine that Heinz wrote in 2000 and going like, hey guys, don't you want to use this? People are going to say like, wow, you're clever. But no, don't do that. Don't be so... Don't copy Heinz from 24 years ago, right? Maybe that was a bad idea 23 years ago. It still is a bad idea today. This is a much better way of doing it. But then what does this do? This basically is a stack of nodes we haven't looked at yet. So basically, when you say next, if nodes is empty, so if you call something else which is wrong here, there's actually a mistake in this code. That is, you shouldn't, if you call next without calling has next, it shouldn't. Could it throw an exception? It actually might be able to throw an exception. It should throw a no such element exception, which it doesn't. So this is a mistake in both of these iterators. So let's add a test here, a simple tree test. We're going to have test void test iteration next empty tree. Okay, we're going to simply say for it equals simple tree.iterator. So we've got an iterator, and we're going to say assert throw is exactly that, no such element exception dot class it next. And my prediction is that both of these are going to fail. So they'll both fail because they'll both throw, or will they fail? They throw null point exception. That's right. So if you poll and it's empty, you get a null point exception. You don't get a no such element exception. So that's wrong. So basically, both of these would be wrong. Both the simple unbalanced and the AVL binary tree both will have a mistake there. So if we go, this of course is the fun part of copy and paste coding, is if you have a mistake in one, you copy and paste it to the other side and you have a mistake there as well. That's why we should never copy and paste code. Right? All right, so one of the things I want to see if there are any comments by anybody. Oops, don't want to do that. let's go to no comments. All right. Okay, so let's try this. So what did I want to do? I wanted to add this over here. So inside here, I want to say if not has next, throw new no-legitimate exception. Okay, and we'll have to copy and paste it over to the AVL tree as well, so that that's there also. So now the tests should pass, I think. Let's try and run the tests. Okay, it's all running happily, I think. And I want to have another quick look at what the actual iteration does. So what it does is it polls the nodes. It then, if the node's left is not null, we add the node left. So basically it's going to go down on the left-hand side, and then return node.value. So if I try this out, let's add a main method in here just to see what would happen. If I say var tree equals new AVL binary tree of, let's say, integer, and I say 0 to 10 tree.add I, and I then iterate through the tree, and I print out the I. What do we see? So let's see what we get from that. So it looks pretty messed up, doesn't it? Doesn't look ordered at all. That's interesting. So maybe it just doesn't. Maybe it's just wrong. Maybe the code's simply wrong, which is quite possible. Maybe it got something wrong in the rebalancing of the tree. It's a bit disappointing because I would have thought. I mean, it's balanced, I guess, but the values are not. It might have not done it correctly. And I'm scared to try the red-black tree. I'll have to try that another time. We've been going for too long already. The interesting thing is that, like, if we probably have to go and look at this one step at a time. Let me debug this, and we'll have a look at what the tree looks like when we get here. So let's debug. And let's see what the tree looks like. So the root we would expect to be not value 3. I'd expect the root to be like value 5 or 4 in the middle. Okay, but for 10 it might be okay. So left is value 1 and 0 and 2. That's correct. And then right is value 7. Left of that should be value 5 and 6. 5 and 4 and 6. Yeah, that's all correct. So it is ordered. It's just the iteration which is not correct. So it's kind of interesting because I wonder if I could ask it to write the iteration for me, because the way that it's doing it here is obviously not correct. What I'm doing here is I basically want to make a recursive iteration, but I'm using a stack instead. So we would need to go left all the way until we hit until we're not null, right? The problem is with the poll. I think that's the problem. The poll removes it, and we don't add it back again. So what we actually need to do is yeah, this is not the way to do it. Okay, so we've got a problem with the iteration. Let's write it again. So we're going to comment this, delete this, and say go to AI, generate code, implement an iterator for this AVL tree, and see how they do it. Let's hope they don't copy Heinz's code from 2000, which was a dumb idea then and is still a dumb idea today. Okay, so I just want to get the iterator. So it's got an AVL iterator. It's got a stack this time. And it's similar idea, but a bit different. Push left tree, push right tree. So let's copy all of this code and see if that works. So this is now the iterator. So we're going to copy that in there and see whether that works. So this is now our iterator, returns a new AVL tree iterator. Again, it's used a stack where it could have used a deck. Equals new array deck. Push left subtree, root. Okay. And the push left subtree, while node is not null, it pushes it in. And then says node.left. So this is a bit different to the way it worked. Let's see if it works. Let's see if it runs. First of all, we're going to try iteration and see it's actually iterating correctly from 0 through to 9, which is great. So yeah, basically our sort of human approach of copying and pasting the code from the other tree, which looked very similar, didn't actually work. What did work is when I said, "Can't you please, can't you please go and test the, write it from first principles." So I'm going to do binary tree test. Let me run that here. So this one, the binary tree test, the simple tree test. Let's run that. In fact, that should be called the binary tree test. And we can see again the max depth on the simple tree is 10,000, and on the other one it's like 14. Okay. Now I wanted to do red-black tree as well, but I think this is enough to look at. Let's just add a comment as well here. And this one should be fairly easy to generate. I'm going to say over here, AI actions, write documentation. I wonder if it's going to explain a balanced binary tree that implements the binary tree interface, AVL property, which shows that the tree is balanced and maintains order log n, time complexity, for insert, remove, and search operations. I actually don't know if the insert, it's probably is order log in, but it's not, I don't believe it's as fast as inserting as, for example, the red-black tree, because the amount of rebalancing is quite substantial. Alright. Alright, I think we'll check that in, and yeah, I'll check it in a moment once I've finished the stream, so I can also paste the linked in stream reference if you want to watch how we got to this. It's hard work. It's hard work doing this with AI because, well, I think part of it is that the tools are still in the infancy. But it is amazing that it actually did the job, right? It did do an AVL tree, which I haven't done for 24 years or so. I haven't written one. 34, no. Yeah, 34 years. No, it can't be that long. Yeah, 34 years. Since 1990. My goodness, time flies. So yeah, so something which I haven't done for 34 years, and it just did it. With a bit of help. But it seems to be okay. I'm still not completely happy with the way the fact that node is not a is a non-static class. I prefer to have a static class, and the way we did it here was let's So let's see what the node looks like over here. The private static class node t extends comparable of t, and we simply constructed it with that. So I wonder if we can fix that before we close. So if we say static t extends comparable t, same as before, we can make a static class, and then we'll have this of node t left and node t right. And then I wonder whether we can fix it. So it's going to be node, this is going to be node, everywhere's going to be node t, so just node. So let's do a search and replace on node. I'm actually scared to do this with AI. I'd rather, in which case, I'd rather do it manually. Exclude, replace, exclude, replace, 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 exclude, 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 replace, replace, replace. Okay, it seems to have worked. Oh, that also has to be done as well. So it's got to be node t of root. So that seems to work, and that's I prefer that, to be honest. I prefer doing it this way, to maybe even renaming this t to something else. So it's not no confusion that it's something, that it's a, maybe just call it e, just to be different to the t. Yeah. So I don't know if one can make these things final. I don't think so. That certainly can't be final, because it gets set whilst you're doing the rebalancing. But I prefer this approach. Oh, this also needs to be done here. I've missed a few. So it's going to be a node of t everywhere. There's node. There's node. And there's at least one place where I didn't need to have the node t because I've used the diamond operator. Yeah, there. Okay, I think we're good. I think we're good to go. Let's run the test once more. I'm going to call this not the simple tree test, I'm going to call it the binary tree test. So it's a binary tree test. Fortunately in Java we have the hash set and the tree set, and the tree set is a red-black tree, so it does a fairly good balancing already. You don't have to implement that yourself. But let's run that and see what comes out. Run them both. Make sure they both work. Of course, the unbalanced one is a lot slower than the balanced one. So that's like 10 seconds. The other one's 13 milliseconds. Amazing, isn't it? Well, I like it. I think it's incredible. So thanks for watching, and please leave comments and share if you enjoyed it. And yeah, I've got lots of other goodies up my sleeves, which we'll look at soon, hopefully. Oh, my watch band is see-through. That's cool. That's amazing. All right. Until next time. Thanks for watching.